So for 1.9, we're going to be looking at rates of change and behavior of graphs. And some of this is going to be recall some of the stuff we've already done and just name it something different. We are going to recall some parent functions and look at them along the way. Then we are going to pick up some new vocabulary to get us going. So I'm going to have two parts. We're going to have rates of change, and then we're going to look at behaviors of graphs. So for part one, I want to look at rate of change. Some vocabulary to get us going is one, rate of change is defined as the change in the output quantity relative to the change of the input quantity. Let's put this in other terms. We already know the words input and output, and we know that output is our y and input is our x. The change of an output quantity relative to the change of the input, well, let's just kind of think about that for a minute. We've done this in previous sections, and I'm going to go on to part two, and I think you're going to understand where I'm coming from as I go further. Average rate of change is the difference in the output values, so the subtraction of the y values of a function, found for two values of the input, x's, divided by the difference between the inputs, x's. So look at all this together. Rate of change, average rate of change. Average rate of change is the change in output over the change in input, or delta y over delta x. Also, y2 minus y1 over x2 minus x1. Having flashbacks yet? This is just slope. We are literally just finding the slope between 2 points. But now we're going to call it average rate of change. And better yet, using function notation, instead of y2, we say f of x2. Instead of y1, we say f of x1. But in all reality, at the end of the day, we're just using our slope formula like we've done before. Examples of rate of change in real life might be some of these examples down here. A population of rats increasing by 40 rats per week. Sorry, gross example there. But that would be a rate of change. A car traveling 68 miles per hour, the distance traveled changes by 68 miles each hour as time passes. That's a rate of change. A car driving 27 miles per gallon of gasoline, rate of change. The current through an electrical circuit increasing by 0.125 amperes for every volt of increased voltage, it's just rate of change. The amount of money in a college account decreasing by $4,000 per quarter, well, that's not good, decreasing. That student must be in college. But the amount of money in a college account changing by $4,000 per quarter, rate of change. So now what we're doing is we're applying the formula of slope that we already know to real life examples and looking at the rate of change from one point to the other. So let's look at it in a table first. So part B examples, the first one we're going to look at, it says using the data in the table below, find the average rate of change of the price of gasoline between 2007 and 2009. Well, here's my table. I'm looking at 2007 and 2009. So let's take it all back to slope. When you're looking at this, notice these values. This would be my x1, y1, x2, y2. I'm just finding slope like we've already done in previous sections. So I'm going to do the change in y over the change in x. So I'm going to say y2 minus y1 over x2 minus x1. So I'm just going to grab my values. I always like to write my formula as a template and then plug in the values I'm missing so I don't mess up these negatives along the way. So I'm going to say, okay, y2, look, I've already labeled it, 2.41. y1, 2.84. Let's see, x2 is 2009 and x1 is 2007. I'm going to just do the computations or arithmetic on the top here. So negative 0.43, 2009 minus 2007, that gives me 2. And this gives me 0.22 negative as an answer. So let's interpret this. This is the average rate of change of a price of gasoline. So this is $2, $2. This is negative 43 cents. This is negative 22 cents. So this means that we have negative 22 cents per year. So that means from 2007 to 2009, we had an average rate of change or a decrease of 22 cents per gallon. Okay, so when we're looking at a rate of change, instead of considering the negative talks about the slope of the line, which it does, it also represents how is it changing. Well, in this way, it's beneficial. The price of gasoline went down. Beneficial to you, the consumer, putting gas into your car. Maybe not as beneficial to the oil companies where the cost of gas has gone down, but we're kind of interpreting and using our formula and our slope to apply it in these different situations. Now, other areas, I was just using from a table, finding my values using formula. Let's look at it on a graph for this number 2. Given the function g of t, find the average rate of change on the interval from -1 to 2. Notice they're using interval notation like we've done in previous sections. And so here what I'm going to do is I'm going to say, okay, -1, that would be my x1, 2 would be my x2, because this is an interval notation, not an ordered pair. So if I want to look at -1, I need to look on the graph here. Notice that it has a y1 equal to 4. And then at +2, I can see I have a y2 value of 1. So I could just do my slope formula again, using these values, using my formula from above, and find that. But I also want you to notice from the graph. Remember we talked about this is the change in y over the change in x. So if I were to start here and go down to this point, I'd be going down 1, 2, 3. So my change in y would be -3 units. Then if I went from my -1 over to 2, I'd be going over, let's see, 1, 2, 3 units. So my change in x would be a +3 or 3 units. Therefore, -3 over 3 gives me a -1, meaning the average rate of change to get from -1 to +2 would be a slope of -1. Notice this is not talking about the slope of the line in between. You can see that's clearly not it. It's talking about if I were to connect these two and create this, what is the rate of change getting from this point to this point, not following your curve, just going straight from here to here, it would have a slope of -1. So I wanted to show you it from the graph, and I wanted to show you how the change in y over the change in x, how I could count that over and then across. Given a graph that's a nice graph, you know, not all graphs have these nice points on them, but also given these two x values, be able to interpret and find these y values and then execute the average rate of change from there, because we might just be working with equation, which we're going to see in the next example. And in your homework, you're going to see this as well. You're going to see where they've just given you the interval, which is just your x values. You're going to have to figure out the y values either from the graph or from the equation. So that being said, let's do that. Let's look at one that just gave us the equation and find the average rate of change. You'll see this in your homework as well. Compute the average rate of change of this function on the interval from 2 to 4. That means this is my x1, this is my x2. So in order for me to do change in y over change in x, I need my y2 minus y1 over x2 minus x1. I'm hoping the more I say it, the more you see it, the more you do it, the more retain this formula, because as mentioned earlier, you will not have any formulas on your exam. You will not have any notes on your exam. So I want to make sure you understand these as we go. So I know I have my x values. I need my y values now. So in order to find what is my y1, I'm going to take 2, plug it into my equation. So I'll say 2 squared. Essentially, I'm finding f of 2. So 2 squared minus 1 over 2 gives me 4 minus a half, which is 7 over 2, or 7 halves. So that would be my y1. Then I want to find my y2. So I'm going to take 4 and again plug it into that equation. So essentially I'm finding f of 4, which would be 4 squared minus 1 over 4. So it gives me 16 minus a fourth. Using my calculator, changing it into a fraction, gives me 63 over 4. Now that I have an x1, y1, x2, y2, I can correctly execute this average rate of change formula. And so I'm going to say 63 over 4 minus 7 over 2. Don't let the fractions freak you out. 4 minus 2. Use your calculator. Use parentheses appropriately. in the top, we end up with 49 over 4 divided by 2 in the bottom, which in your calculator, this would give me 49 over 8. So just don't let the fractions freak you out. Do what you know how to do and work from there. Now in part 2, we're going to be looking at behavior of functions. Now that we know domain, we know range, we know what we're doing with average rate of change, we're going to kind of put it all together. So to get us going, first let's look at some vocabulary. First of all, I have some vocabulary of what is a local maximum. This is a value of the input, or x's, where a function changes from increasing to decreasing as the input value increases. So this is a value of x where a function changes from increasing to decreasing, going up to going down, as the x value increases. Local minimum is a value of the input, or x's, where a function changes from decreasing to increasing as the input value increases, or as your x increases. And local extrema is collectively all of a function's local maxima and minimum. That was a lot of words for a math class. Let me show you in a picture here. So you'll notice here with this function here, it's increasing or it's going up. Remember, we read a graph from left to right, and then it's going down. You can see that it's created this point here where it changed from going up to going down. This is known as a local maximum, or all of them together a local extrema. Likewise, look at this graph. It's going up, it's going down, so there would be a maximum, or a local maximum. It's going down, it's going up, so down here would be a local minimum. Together, we could say the extrema of the graph are at this point and this point. And so you can see here it says local minimum is at negative 16, and you can see it occurs at x equal to 2. And so when we're talking about local maximums and minimums, we're talking about these highs and the lows, and together those highs and lows are called extrema. Next thing I want to clarify is increasing function. A function is increasing in some open interval if f of b is greater than f of a for any two input values, a and b, in the given interval. Got a lot of extra letters here, where b is greater than a. So basically, it's just like what we're seeing here. As our y values are increasing, as our x values are increasing. But I want to give you the basic definition like the book gives you. A function is decreasing in some open interval if f of b is less than f of a for any two input values, a and b, in the given interval where b is greater than a. So this means your y's are getting smaller as your x's are getting larger. Now all together, we kind of generalize it and we say we have an absolute maximum, that's the greatest value of the function over an interval. If it's the highest point ever, that would be your maximum. Or absolute minimum, the lowest point ever. And so that's the lowest value over an interval. So all this being said, I'm going to do some examples with this. I want to go back to our parent functions like I've done in the last two sections. Notice our constant function, it is neither increasing nor decreasing. It's a flat line. We only call it like we see it, and that is not doing either. The identity function, notice just the parent function itself. We're not talking about all its children, just the parent function itself, y equals x. Left to right, you can see it's increasing. Quadratic function, we can see that our parent function here is our u-shape. It is increasing from 0 to infinity. So from 0 to infinity, it's increasing. And it's decreasing from negative infinity to 0. You'll notice wherever it stops increasing or decreasing, we only put a parenthesis there, because at that point there, that is a minimum at 0. So in any of these intervals of increasing or decreasing, you're always going to use parentheses. You're never going to use a bracket. Next, the cubic function, it's always increasing. It looks like the increasing kind of slows down here in the middle, but this is considered always increasing. The reciprocal function here at the top, it is increasing, never. It is decreasing from negative infinity to 0 and 0 to infinity. And again, that goes back to our domain issues. The reciprocal squared, it is increasing from negative infinity to 0, decreasing from 0 to infinity. The cubic root, This one is like the cubic. It's always increasing. Square root is from 0 to infinity. It's always increasing. Goes back to domain. The absolute value function is increasing on the left. It's decreasing on the right. And it has a minimum at 0. And again, you can see we did not include 0 in that notation with increasing, decreasing. So all that being said, let's do some examples. So part C, examples. Given the function p of t in the graph below, identify the intervals on which the function appears to be increasing. So we're just looking at the graph. We're looking at where is it going up. So you'll notice here is where it changes from going down to going up. Here is where it changes from going up to going down. Here is where it goes up again. So it wants to know, where is it increasing? Right here it's increasing. So I'm going to say from 1 to 3. And then over here it's increasing. So I'm going to say from 4 to infinity. And so I would say that it's increasing from 1 to 3, union with 4 to infinity. Still using that interval notation. Number 2, consider the function graphed at right. And I took this straight out of your textbook. You're going to have homework problems just like this. Consider the function graphed on the right. The function has and it wants me to select an answer, either minimum or maximum. Notice it has a maximum, an absolute maximum actually, right there. And it says of, so it wants your y value, 2, at x equals, and so that x value is -1. The function is increasing on the interval. So let's see, from here to here it's going up. So we would say negative infinity to, and we use our x values in these notations, so -1. It's decreasing over here, so from -1 to positive infinity. Let's look at another one of those, and we'll end our talk of increasing and decreasing. The function has a, notice down here, minimum. Of, we're looking at y value, and I've kind of scribbled through it there, but it gave me the y value of negative 2.25 at, and it also gave me the x value there. It's kind of small print, but that was 1.5. Then it says the function is increasing. So notice from this point on, it's increasing. So from 1.5 to positive infinity. It's decreasing over here on the left, so I would say negative infinity to that 1.5. Notice I'm still using interval notation, parentheses there when it gets to 1.5. Then it asks me domain and range. This is a quadratic. Notice it has that U shape. The domain of all your quadratics are negative infinity to infinity. And the range would be from this point up. So starting at negative 2.25. And we do have a value there, so bracket, comma, positive infinity. So I really like a question like this because it's kind of put everything together. Domain, range, minimum, maximums, increasing, decreasing, and it's still using that interval notation. So I hope 1.9 goes well for you. If you have any questions along the way, feel free to Canvas message me, ask me specific questions about the homework, or if you need more details about increasing, decreasing, or rate of change, feel free to just holler at me. Hope it goes well.